Hello, everybody. So it's time for our today webinar. We will just wait a little bit for everybody to get connected, and then we will start in a few seconds. So I can see that some of you are already connected, so it's great. You know that we have the live chat where you can write your question or share a YouTube. So we will be able to answer you either on the chat or at the end of the webinar with question and answer time. Okay. Maybe I'll switch to the presentation mode and we wait just a little bit more. So you should normally see the slides that we are presenting, and you should see two faces from us, from the presentators, on your corner. If you have any issue, you can warn us into the chat so that we can try to help you with some issue you might have. Okay. Let's go into it. So today we are going to make a webinar about CANUNDA SPLIT. So we are going to be two to present the webinar. So Jian, that you can see, she's the VP Product Management and Partnership at Cailabs. And myself, I am International Sales Manager for the product CANUNDA. So I guess, yes, what do you think, Pooh? We can start? Yeah, great. Okay. So today we are going to talk about CANUNDA split and about laser beam splitting for micromachining efficiency. This is the theme of our today webinar. We will first present you the split technology. We will then, Pooh will then present you some results and application, and we will finish by a question and answer time at the end of the webinar. About 20 minutes or something like that, so that we can have really live exchange together about the question you might have. Okay. To introduce the webinar, I will start with the first introduction about Cailabs, if you don't already know about Cailabs. So Cailabs, we are a French deep tech company. We are located in Rennes, in Bretagne, in France. All of our products are based on the MPLC technology. It is our core technology, which is patented. We have today more than 19 patents on that technology. And we are about just a little bit less than 60 people now. We have finished the last fundraising last year. And so that led to some growth into our teams, which lead us today to this almost 60 employees. As you can see below, we have several companies that trust us and which we work with, such as Safran and Amplitude. I guess that you might already know this company. Our technology, MPLC, is used in several product lines. The CANUNDA split is part of the CANUNDA line, which is dedicated for laser material improvement solutions. We'll discuss about that just a little bit later on. We have the product Aruna, which is dedicated to improve the network for of local network. We have the product Tilba, which is dedicated to free space communication, such as, for example, Earth and satellite communication. And we have our custom solution, which are made for every very, very specific application. And in that department, we have also made what we call Proteus, which is a solution dedicated for lab application for MUX and DMUX. And in this tailored solution, we also have defense applications and things like that, for example. And all of that is with MPLC. So MPLC stands for multi-plane light conversion. You may have seen some papers about that before, but let me just represent you shortly that technology. Okay, so what we do at Cailabs, we change the shape of the light, and we change it by sinking into a mode. And that's what you can see on the below picture, where we have multiple beams as an inlet, and plane by plane, we will change the shape of the light until we get at the end to the final required shape. On this example, on the left side, it is done in a transmissive way, but finally we decided to do it in a reflective way that you can see on the right side. This is typical example for telecom application. So at the end of all of this reflection, we have beams that has been shaped. What are the main advantages of this MPLC technology? We can shape any shape you want, like asymmetric shape or any very specific shape you require for your presses. It is a passive technology, so we have no loss. It is a reflective technology, so we can handle very high power and very high energy. And we can also handle multiple beams as an inlet. I have one beam at the outlet or the opposite. And we can also shape multiple beams simultaneously. So this is the MPLC, which is used for all of our product and which is used for our CANUNDA product for laser material processing improvement. So why did we get to this CANUNDA product range? Today it is quite known that the beam shaping is a key to improve the yield of laser material processing. But the beam shaping is also has some challenges because some very important points need to be successful so that everything is going well into the final application. So first, about factory environment. So you have noticed that if you work in a factory environment, it is different from when you work into a lab environment. And so we have developed our system to be compatible in real application. So we can be used in a rough environment or industrial environment. Our design is quite compact, it's ready to use, and it's compatible with the common equipments you can find in a customer application, such as the scanner, f-theta lens. We are, of course, compatible with ultra-short pulse lasers, things like that. Then we also, as you might have seen, we are facing to some instabilities of the laser, which can make the beam shaping quite difficult because of tilts or shifts, power variation, and so on. So what we do with all of our product, we help stabilize the laser inputs. So what we do, we remove the tilt and the shift, and the shape we deliver has a very good energy homogeneity. So it makes the beam shaping more reliable. And that also what we do with the depth of focus, because most of the process needs some flexibility regarding the focus point. So they need to have quite a high depth of focus. And that's what we do also with our product. Our technology allows to have one of the highest depths of field in regarding to the other technology. So we are quite equivalent to a beam that has not been shaped. So this is really the three major points of our product. And this product, we have organized them into the product range that you can see here, that I will present you shortly. So we have the CANUNDA hexagon. It is a reflexive hexagon, which helps you, which creates a bezel beam and very high quality bezel beam. Because we control the geometry of the hexagon very well, the bezel beam that we generate is really close to a theoretical one. So it leads to very good quality in terms of cutting or drilling, for example. This is dedicated for ultra-short pulse laser and available in various wavelengths. We have the CANUNDA pulse, the one that you see at the top right corner. The CANUNDA pulse is a module that we have done in order to make beam shaping, like top hat beam shaping, round, circle, line, or any custom shape. And this module includes the stabilization I just presented earlier that we called mode cleaner, which allow to remove the tilt and the shift from the laser source. We have the CANUNDA split. The CANUNDA split is really the topic of this webinar today, is a way of beam splitting for increasing micromachining efficiency. And this is also for ultra short pulse laser. Oh, I forgot to mention the CANUNDA pulse that I just showed you before. This one is available for IR and will be available for next year in green and the following year in UV. And the CANUNDA split, I will show you that later on. And the last product, the CANUNDA HP, is a system we have designed in order to shape the beam for continuous high power laser. This module that you can see here can handle up to 60 kilowatts. We can shape the beam and we can also work with stabilization. So this is to give you a full picture of our product, and now we will target here, especially on the CANUNDA split. So CANUNDA split, as you can see on the picture, it is also what I have here with me. This is the module, so you can see it is quite compact. You just can use it into your setup, so it is ready to be used. Why did we get with this product? So now micromachining is used, laser is used more and more with the micromachining, with a very, let's say, wide range of application that you can see here, such as engrabbing, cutting, drilling, welding, surface structuring, and thin film removal for this application that you can see. And what we have seen is, with the time, the power of the laser gets higher and higher. The price remains the same, but the power is increasing. And so it is good, but that's not the only way. That's not the only way to increase the productivity, because the main topic is to increase the yield of the laser material processing to make it more reliable and more valuable for other industrial processes. But then, if you always use more and more power, what you will do with that, or how can you try to increase the productivity with more power? You can try to either increase the pulse per energy or to increase the rep rate. But the problem is, for ultra short pulse laser processes, it's not always the correct solution. Because if you increase the pulse per energy, as you may already know, you may get a bad quality of process or lower quality of processes. And if you increase the rep rate, you may have some heat accumulation. So that's not always the best solution. So what can we do to increase the yield of the processes? There are several solutions. To increase the yield of the processes, we can increase the processing time. For example, by increasing the scanning speed. And this is why all of our systems are compatible with scanners, so that you can use scanners instead of moving table, for example. You can improve it by having beam shaping. We know now that with specific shape, your processes have a better yield. And another solution is to have parallel processing with beam splitting. That's what you can see on the picture. And the principle is quite simple. Instead of processing an area in one time, you do the same, but processing several areas at the same time. So by doing that, you increase the speed of the process and you increase the yield. So this is really the core of the beam splitting that we have designed. So splits benefit that we got. What is the specificity of our product? We have a product which is quite flexible in terms of splitting, because you can choose in between several patterns. So you can then, one module can be compatible with several processes. Another important point is homogeneity. We have very good homogeneity in between the spots that have been splitting. So it allows you to have a reliable process. And our module, they are easy to integrate. So you can see the design is compact. It is compatible with ultra short laser, and we don't have chromatic effect. It is compatible with fast scanners and with FT-Talents. So this is the three major benefits that we should keep in mind by thinking of CANUNDA splits. But then I also would like to present you maybe more in detail what is inside the CANUNDA split, or at least how does it work. So the CANUNDA split now is a module that is available for the wavelengths that you can see here, the 512, 530, 1030, and 1064 nanometers. Of course, if you have a wavelength which is different, we can always think about making a custom system for you. Because as we are, let's say, quite a flexible company, we are always interested to have custom application to fit to your needs. So we are really open to adjust the configuration of our standard equipment to fit to your specific application. So splitting we do is a high quality splitting. We say so because, as I mentioned earlier, we have very good homogeneity in between the spots that have been splitted. We have 98% homogeneity, and we have over 90% transmission into this module. And this module, so we have two configurations that you should choose before to get the system. Either you choose to have the variable pitch configuration, either you choose to have the multi-pattern configuration. How does it work? So the system includes a neutral pattern where if you just want to have your normal process without any splitting, okay, you choose this pattern, it will do nothing. And then we have 5 patterns with variation to the pitch. This is the angle that you can see here as a separation angle in between the spots. I will talk to you about that a little bit later on. So this is a variable pitch, so it is sequential position. Or you can choose a multi-pattern configuration. On that case, you still have the neutral pattern included, and you have 5 other different patterns. So we have one pattern which is division by 5 vertical, division by 5 horizontal, then you have division by 9 vertical and or horizontal, and the last one which is a splitting 7 by 7 matrix. This is helpful because one machine very often works for several processes, and so you don't need to change the module. The module remains here, you just need to change the pattern. And again, if your patterns are not exactly the one I mentioned here, it is possible to have a custom configuration for you. How do we change this pattern? We do it by an electronic way, and it is with a USB switch connection. So really easy. How is it integrated into the process? So you can see here a typical setup where you can use the CANUNDA split. So you have a laser that can get with a Gaussian beam. Then we have an ejection telescope because our module handle an input beam waist of 1 millimeter. So we need this size to have our system to be able to split the beam. And then we have a combination of lenses, scanner, and f-theta to get the right size at the sample and also to scan your process. And this combination of lens give you the final pitch and the final spot size of the beam splitting at the sample. So you will see later on with Pooh, which will present you typical setup with typical spot size and pitch that we can get. And also important point to mention, you can download our spec sheet either on the website or you can send me an email so I can send it to you, where depending the focal lenses of the optic you use, that gives you the typical spot size and pitch that you will get at your sample. So easy to get this information. Important point to share here is about the other characteristic of the system. So our system can handle up to 300 femtosecond pulse duration, up to 1 millijoule, and with an average power of 60 watts. And below it's the dimension which are mentioned, but you can see it is exactly the same size as the module I just have here. So this is for the CANUNDA split. And I think, if I am not mistaken, that now it is time for a small poll to have some interaction together just before that Pooh presents you the application. So let me try to activate the pool time. Okay, so you might see the question now. Pooh, can you just write me if everything is working correctly? Great. Okay, perfect. So you see the question. So what we wanted to discuss with you is if you have already thought about using a beam splitter. Okay, so that is the solution that we propose you that you might have tried before. So yes, I would use a beam splitting, but I could not find the right solution. Yes, I have studied or tried a SLM solution. Yes, I have studied or tried a DOE. Yes, I think your beam splitter might fulfill my needs, or no, I don't need a beam splitter. So we have also asked you that kind of question so that we can also maybe better present you the main difference in between the several system, or maybe yeah, discuss about that. So let me check how many people answered according to how many people are connected. Okay, so we are almost a little bit more than half of you have already answered the poll. I let you maybe just a few seconds more. Okay. Maybe it's just time to close the vote, and we share the results. So I'll let you 2 seconds more if you just finally want to vote, but I think we are good. Okay, I'll share the results with you. So what we could see. So 1 of you couldn't find the right solution. 3 of you have studied or tried the SLM solution. 5 of you DOE. And 1 of you think that a beam splitter could be good, and 1 of you don't need a beam splitter yet. Okay, so maybe it will take a minute to comment that. To give you an idea, the main difference between SLM and our solution is that our system, as we are multistatic, we can be considered as a little bit more reliable through time, for example. And regarding DOE, then our main advantages is our flexibility in regard to this DOE. And for these 2 solutions, another important point to consider is the final efficiency of the system. I have showed you before the efficiency of transmission and the homogeneity in between the spots. So this is 2 high values that may be very good for your processes in comparison to these 2 other solutions. So if you have tried these 2 solutions and you maybe are not happy, or if you would like to see in more detail what would be the differences, please feel free to send me some chat question or then send me an email, so maybe we can discuss that in more detail. Great. I'll stop sharing the results and I'll get back to the presentation mode, and it will be who that will speak. Okay, well, I'll speak later on. Bye-bye.
Thanks, Tiphaine, for the first part of the presentation. So to continue on this webinar, I'm going to present to you some application results that we had with our beam splitter. And these application results were obtained with LASEA for thin film removal. So just a few words about the process that we tried to improve with our splitter. The idea with LASEA was to improve the ablation of a small thickness of some thin films of some surface in a very highly localized and selective way without damaging the substrate. And so this is done with a very small spot focused on the process with ultra short pulse lasers. And so the idea was that to do this kind of thin film removal, you actually don't need necessarily very high power, but you could improve the process, the yield, the throughput of the process by splitting the beam, splitting the energy that you have into multiple beams in order to do parallel processing in the process. The way we have done that was so by using a CANUNDA split. So let me try to have a pointer to show you how it works. So this is an image of the setup that we had. So we used an amplitude Tangor laser as the laser source, which was treated with an LS shape module by Laser. And with this Gaussian beam in input, we put it into a CANUNDA split module in order to get 9 splitted beam, a single line of line splitted beam at the output. So we obtained 9 beams with pitch, so a distance between the beams of 1 millimeter at the output of the CANUNDA split. And then we used a transport telescope between with one lens, sorry, LS scanner, high-speed scanner from Laser, and an f-theta lens of 100 millimeter focal length. And at the end, we obtained very small beams that were focused on the processing plane with a distance of 160 micron between the beams. And we have analyzed first the quality of the beams that we obtained at the output. The first thing is that we maintained a very good depth of focus of the splitted beams. So basically, the splitted beams were Gaussian beams, and we measured that the depth of field of these Gaussian beams were exactly the same as the equivalent Gaussian beam if there were only a single beam. So we measured a depth of field over more than 1 millimeter. So this is exactly the same as the rated range of the equivalent Gaussian beam. Then we analyzed the quality of each single Gaussian beam. And what you can see here is that we measured a very good homogeneity between the beams. So as you can see on the top right drawing here, you see that the intensity of each of the splitted beam is exactly the same. And there's no deviation, for example, for the peripheral spots. So we have a very good homogeneity over the whole range of the beams. The homogeneity was measured to be plus or minus 2% in this case. And we measured also a very low loss. So the whole system introduced only 1% of loss in this case. And as you can see also on the bottom part, the beams are extremely well preserved in terms of shape. So they are still very round shapes, very round beams, sorry. And there's no, for example, ellipticity that was introduced in the peripheral spots, which is something that could happen when you use, for example, a DOE for splitting the beams. So in our case, you have very, very good quality, and you're basically sure that every single beam in the splitted beams are exactly the same. So these images were taken right after the system, so before going through the scanner and the f-theta. And if we look at the images after the f-theta, so on the processing plane, we can see that the quality of the beam is preserved after transmission through the whole field of view of the f-theta lens. So these images are exactly the same whichever place you are looking at on the processing plane in the field of view of the f-theta lens. And we still measure a homogeneity of plus or minus 2% after going through the f-theta lens. We still see that our beams are very round, circular, so there's no ellipticity that has been introduced into the system. And we are getting at the processing plane beams with a waist of 17 microns, so very focused, very small beams with a pitch, a separation between the beams of 160 micron. So what you can observe here is that the beams that we obtain, the splitted beams that we obtain, can perfectly go through all the optical chain. They go through the apertures of the scanners, they go through the aperture of the f-theta lens, which is sometimes a challenge when you make splitters, beam splitters with DOEs, for example. And in our case, we managed to get beams that are transported, that are propagated without any clip, without any issue through the apertures of your industrial setup. In terms of process, you can see here the results. So the idea was to decoat molybdenum coating over steel. And what Lasea managed to do with our beam splitter is to obtain a single pass decoating over their sample with very parallel lines, thanks to the homogeneity of our beam splitter. And the immediate result was that the throughput of the process was increased by a factor of 9 thanks to our system. Well, this is an easy calculation since we had 9 beams, but because the quality of the beams was extremely good, the fact that we splitted the laser into 9 separate beams didn't decrease the quality of the process, and so we get immediately a factor of 9 in terms of throughput increase thanks to that. And just to show you some result of the decoding, unfortunately it seems that the video is not working, but you can see the sample on the right side of the decoding. So this was obtained, the 2 logos of Lasea and Cailabs were obtained by using these splitted beams to decode the sample. So this is one idea of application of how to use our system. Basically, in any case, any microprocessing application that you have, if you have enough power to be splitted, to be distributed over for parallel processing, we believe that our beam splitter is the best way to go in order to improve the throughput of your process. And what we hope is that after this webinar, you have, well, you will take home the message that what we can offer with our CANUNDA split is a very flexible beam splitter, where you can choose different patterns depending on your application. So either different patterns of different configuration of spots, or with different pitches between your spots. This can be very useful, for example, if you are changing different material between use of your machine. That's also that you will remember that our system offer a very, very good homogeneity. So we offer basically the same quality of beam as the unsplitted beam before. So you can maintain a very good homogeneity of beams over the full view of full field of view of an f-theta lens. And these beams also can go through all the optical components that you have on your industrial setup, which leads to a very simplified machine integration. So you have a splitter that is completely compatible with your industrial machine. We have showed before that it was compatible with Lasea components, but it can also be Lasea modules, but it could also be compatible with any scanner, any f-theta. And so we can offer a splitter with no chromatic effect, no ellipticity on the beam, that is compatible with fast scanners and f-theta lens. Thank you for your attention. Now it is time for your questions. So I see that there are no questions yet, but please, we will leave you a few minutes to write some questions. Okay, so there are some questions arriving. Okay, let me post the question. So the question is from Jian. How do you optimize the different spots in terms of homogeneity and ellipticity? Since the MPLC is passive, do you need to customize several MPLC adapted to the input laser until it works? This is a good question. Actually, no, we don't need any optimization. So our system is intrinsically preserves the homogeneity and the quality of beam of the input. So obviously, if your input beam is elliptical, for example, then the input laser is elliptical. We are not going to correct that with our system because it's passive. However, from at least from all the tests that we have done, and by design, the MPRC preserves the homogeneity of the input beam and preserve the ellipticity of the input beam. So there's no adaptation, no customization that is needed in order to make it work for a given input laser. We have another question from Olga. So is it possible to rotate the configuration? Yes, so it is possible. So first of all our configurations are adapted to the angle of that is introduced by the scanners. So as you may know, scanners usually introduce an angle of around 12 degrees. And so all our splitters are adapted so that the beams are all parallel in the processing plane. And for example, in the configuration where we can offer different patterns of pitch of splitting, we offer the possibility to have a pattern which is a horizontal and another one that is vertical. If you go through for customized configuration, we can also offer different angles. For example, if you are interested in something that is, let's say, rotated by 45 degrees, this is something that we can offer. Sorry, I think there's another question. Yes, so a question about the technology. So is this technology based on multiple beam splitters inside the CANUNDA split? And what about the direction of polarization in that case? So this technology is not based on multiple beam splitters. It's based on our own technology of multiplane light conversions. So there's no beam splitter in our technology. It's purely reflective technology where we use different phase planes in order to change the beam shape or the beam splitting. And our technology is intrinsically polarization independent and polarization maintaining. It means that whatever the polarization of the input laser you are using, what we offer at the output is the same, exactly the same polarization. Another question, is 9 the maximum number of beamlets in line, or could it also be increased with the customized solution? Yes, Daniel, it's perfectly possible to increase the number of beam in the splitter in customized solution. To be honest, for the moment we offer 9 because from all our customer feedbacks for the moment, the main limitation becomes the available power. When we go above 9 beams, most of our customers say that it's not useful because they don't have enough power anymore in the processing plane. But if in your application you need more than 9 beams, then it's possible for us to increase that. And another question from Johan. Our main example is with USP lasers. Is there a limitation with higher pulse duration? No, there's no limitation at all with higher pulse durations. Actually, it even makes the system simpler because there are less constraints in terms of maintaining the pulse duration. So there are less constraints in terms, for example, of coatings that we need to use in our system. So it's actually even easier if you want to go with higher pulse durations. Another question. Can you maintain the spot pitch over different scanner angles? Yes, it's possible to maintain the spot pitch over different scanner angles. The limitation becomes the f theta at some point, so it's better if you have a telecentric f theta, of course. We can't go against the physics of the existing optical modules that you have on the industrial setup, but from our system, the point of view of our system, yes, we can maintain the spot pitch. Does the pitch of spot size depend on design or f theta lens focal length? The pitch, well, the ratio between the pitch and the spot size doesn't depend on the f theta lens. This is something that is designed. It may depend on the size of the input laser beam, but it's not dependent on the optics after the CANUNDA split. However, the exact size on the processing plane. So let's say you want, I don't know, a waist of 100 micron and a pitch of 300 micron. This is dependent of the f theta lens. So this ratio of 1/3 is maintained whatever the f theta lens you use. But if you double, for example, the focal length of your f theta, you will obviously change the size of the spot and the size of the pitch. So we basically offer a ratio of pitch versus spot size, and then the exact size on the sample depends on the design of the optical elements you have after the CANUNDA split. Another question, you mentioned constraints in pulse durations. Did you see a stretch of the pulse duration on USP lasers, and did you completely correct it? So actually, we did not see any constraints exactly on the pulse duration in terms of stretching of the pulse. The constraint of 300 femtoseconds that we mentioned, it's mostly a constraint on the coatings that we used, in the sense that if you want to go to lower pulse durations, we would need to change the coating used in our standard configurations to be able to cope with these shorter pulses. However, our system itself does not introduce any chromaticity, so there's any chromatic effect. So there's, even if you go to lower pulse durations, let's say, for example, 100 femtoseconds, you would not see any chromatic effect in the system. Another question, so is your beam splitter capable of beam combining when the beam enters from the opposite side? That's a good question. In theory, yes, but you would need to, this would be a coherent combination that you would need to do. So it means that you would need to control the phase of the input beams in order to combine it. This is something that we actually offer with our MPLC, but for completely different applications than industrial laser processing. We do have a webinar that was done with the ONERA, so the French aerospace lab, on the topic of beam combination, and invite you to look at this webinar if you want more information about how beam combination work with MPRC. But the short answer is yes, it's possible, but you would need to control the phase in order to obtain a coherent beam combination. If you want to do incoherent beam combination, it's also possible with the MPRC, but it would be done with a completely different system. Okay, I think there have been, there's still another question. So, can you combine top hat with the beam splitter? Yes, it's possible. So the beam splitter preserves the input beam. So we've done what we have shown for the moment. All the applications that have been done was with a Gaussian beam at the input, but it's also possible to use it with a top hat beam in the input. And we do have a line of products to make top hat beams, which is called CANUNDA Pulse. So it's possible to combine both. However, the fact that these are top hat beams change a little bit the properties of the beams. So all the parameters that we have given in terms of homogeneity, in terms of apertures that we can go through, may change a little bit depending on the beam shaping that you put in front of the beam splitter. Tiphaine, maybe you want to answer that part of the question?
Yes, for sure. So what is price range for beam splitter? Good question. The module that you can see here is a standard configuration. It's about 12 to 15K. And then, of course, if you want a custom configuration, then we need to discuss. So that is the current pricing for such a system. But to have more detailed quotation, please get into us, and so we can discuss about your needs and see if it's which configuration would be good for your application. Okay, maybe I'll let Pooh answer to the coming question. But I don't know if the so Kiran Kabutu asked, what is the aspect ratio?
I'm sorry, I'm not sure I understand completely the question. So we offer different ratio between the spot size and distance between the spots. I'm not sure if this is the question, if this is what the question is related to. If so, the ratio that we offer go from 2 times basically a separation of 2 times the spot size to 4, 5, 6 times, depending on the configurations. And of course, we can customize that depending on the application. Okay, I think there have been a lot of questions. Thanks everyone for your participation. I hope that we have answered most of your questions. If not, don't hesitate to contact us at these 2 email addresses. And you will receive a link to watch the replay of this webinar right after we close it. So again, thank you very much for your participation, and hope to talk to you soon. Thank you.
And yeah, thank you to everybody, and bye-bye. Feel free to contact us.